This video is going to be on objective number 5. Explain the 5 basic measurement quantities. I'm going to go over this objective with the PowerPoint behind me, although I'm not really going to use the PowerPoint a lot of times. So if I'm standing in front of words or something that you need to see, feel free to pause the video at a point where you can actually read it and then continue playing it. Or if you're having a hard time reading something, remember you can go to my webpage and you can find the actual PowerPoint with the notes that go over what are the 5 basic measurement quantities. So, what does it mean to be a basic measurement quantity? Well, you're going to just do one thing. It's simple. It's basic. So you're just going to try one thing and then you get your measurement. The 5 basic measurements are mass, weight, length, time, and temperature. So let's start with the first one, mass. Mass has to do with how much material or matter is within something. So for example, you pick something up, you pick up a rock or whatever, and you can feel it's got mass to it, it's got some heft. Some things can be deceiving, like if there's somebody that's never seen styrofoam, they see a large piece of styrofoam and they go, wow, that's big. It should be very massive. But then you pick it up and you go, wow, it doesn't have a lot of matter in it because there's a lot of air in it. Because of things like this, people can be tricked. They're not quite sure what the mass may be. So that's why we have to use instruments. So an electronic balance, you can put an object on there and it'll tell you how many grams or ounces the mass is. Right? And we also use a triple beam balance. A triple beam balance is a great way to show the idea of mass, because you want to know how much matter this contains. You put it on here, you slide the riders across until you get it into balance, and that will tell you how much matter there actually is. So balances are used for measuring mass. As I mentioned, the metric unit is going to be grams. The problem with a gram, and that's going to be really hard for you to see, right, is a gram is tiny. So if you're measuring paper clips, you can measure in grams. What scientists most often want to do is take 1,000 of those. Think about what we did with the metric system. If you have 1,000 grams, what's the prefix that's going to go in front of the gram? Great, kilo. So here is 1,000 of those little tiny grams. This is 1 kilogram. And this would be much more helpful as far as finding the mass of a rock or a mineral. That's mass. Next one is weight. Weight deals with how much gravity is pulling on an object. So it's not comparing a balance, all right? It's how much gravity pulls down. So we use scales to measure that. Like if you go in the bathroom to find out what your weight is, you step on one thing, the bathroom scale, and it'll tell you how many pounds you weigh. Another example is a spring scale. Spring scales, if anybody's a fisherman, right? You hook the fish onto the scale, the spring comes down and it tells you how much gravity is pulling. That will tell you how many pounds, or in the metric system, it is newtons. Okay, so weight, we said, but depends on gravity. Well, what causes gravity? Gravity is the traction with the earth. So how are you going to change your weight? You got to affect the gravity. You have to change your position to earth. So how do you do that? Well, let's go up in an airplane. Let's get away from earth. Well, I can't do that in this classroom. So how about if I jump up on top of the desk? So now I'm further away from earth. Not as much as going up in an airplane, but I'm still a little bit further away. So if I get further away from earth, like going up in an airplane, as my distance goes up, what's going to happen to my gravity? Well, if you've ever thought about somebody up in a rocket, right, astronauts, as you get further away, your gravity goes down. As your gravity goes down, your weight goes down. Now technically, I haven't really moved that far from the center of the earth, so it will only go down, decimal points, a fraction. But it still will change, it will decrease. So if you're up in an airplane, farther away from the earth, less gravity, less weight. But what about the mass? What about my mass if I am in an airplane? Well, what about me standing here? Jumping up on the desk, has my mass changed? I don't think so. Not unless I lost an arm as I jumped up on the desk. Right now, oh, it's not the same Mr. Oliver, he doesn't have the same amount of matter. So unless you change your object, the matter, the mass will remain the same. Okay. What about going to the moon? Right? Well, is the moon going to have the same gravity as Earth? Is the moon the same size as the Earth? No. So since the moon is smaller, take a guess. Will the moon have more gravity than Earth or less? Well, the moon is smaller, it will have less gravity. Okay. Now, if the Earth has less, or the moon, excuse me, if the moon has less gravity, what will happen to the weight of you or me on the moon? Less gravity. If you said less weight, nice job. Now, what about your mass on the moon? If you said stays the same, great, right? Unless on my flying to the moon, I bite off all my fingernails and I cut my hair and I lost an arm, all right? If it's still the same person, my mass will remain the same. Now, if you want to be technical about it, the moon is about 6 times smaller than the Earth. So if it's about 6 times smaller, that means your weight would be 6 times less on the moon. So for an example, if you weighed 120 pounds on the moon, you'd only weigh 20 pounds. Next basic measurement is length. Right? Length is the distance between any 2 points. You can say length, the width, the height, it's all the same thing. We use either a ruler or a meter stick, right, for measuring the length of something. You know, the length of this table, the width of the piece of paper. Yes, you probably measure in inches or feet, but in the metric system we are going to use meters. So the basic instrument is the meter stick. Right? So on one side it'd be in inches, on this one it's 1 meter. Okay? And remember the idea of what we were doing when we were converting, so that if you measure something in meters and you say, I don't like that in meters, I want it in centimeters, you can move the decimal to convert from meters to centimeters or to millimeters or to kilometers, kilometers, and such. There are 2 examples in your notes that I would like you to just pause the video and try those to make sure that you still feel comfortable moving between the metric system. You can check answers with me tomorrow on those 2 if you don't feel comfortable. That is length. Next basic measurement is time. All right, time is basic because you only need to do one thing. Right? You can look up one measurement. In class, we're going to use a stopwatch, right? And we will measure it in minutes and seconds. But obviously, you know there are lots of measurements for time, not just minutes and seconds, but days and weeks and months and years, and in earth science, millions of years. The definition of time is up here, but basically time is just how long something occurs, something happens, or something happened, like in the past, or how long for something to happen in the future. It can be an event, like how long did it take you to run? It could be something that has transpired, like how long did it take the process of forming the Adirondack Mountains? Or a condition, like how long have you been on this planet? So those are all time. On page 15 of the reference tables is 2 very important earth science times that I want to make sure that everyone understands. Page 15 is the solar system data. When you check out the solar system data, you want to find Earth. When you find Earth, you want to go over to period of revolution. And once you do that, find Earth, come over to period of revolution, you see 365.26 days. That's not an exact number. So, well, 365 days, what's that? How long is 365 days? I'm hoping you're saying a year. That's how long it takes the Earth to revolve, a revolution, to go around the sun once. 1 year. So that's how we have 365 days in our year. And it's a decimal, right, which is about a quarter, which is why we have leap years. Every 4 years we have to add in 1 more day to make up for that decimal. So the whole idea for time in our calendar, a year, is because of how long it takes the Earth to go around the sun. Check the next R word, and be very careful you don't mess with the R words, revolution, rotation. Rotation, Earth, 23 hours, 56 minutes. Right? Round that off, it's about 24 hours. Well, how long is 24 hours, guys? Oh, it's a day. So 1 Earth rotation is 1 day. And again, that's right, what is determining the sunrise and sunset, and the fact that the Earth is spinning, it's rotating. So our time is all based on the motions of the Earth. Make sure you understand the words rotation, revolution. Rotation's a day, revolution a year. The final basic measurement quantity, temperature. Your review book is going to have in the glossary definition for temperature how hot or cold something is. Really lame definition. Don't like it at all. And I'm going to show you a little demo. I'm going to have a volunteer come in a second. We'll do a little demo to show why I don't like that definition. I like this definition much better. It's a measure of the average kinetic energy of the particles in a substance. So how much kinetic energy they have. Kinetic energy is the energy of motion. So are those particles moving fast, or those particles moving slow? That is temperature. And that's not something you can just easily determine. You need to use a thermometer, right? Outdoor thermometer. In lab class, we're going to use the thermometer. It looks like this. We will measure in Celsius, the metric unit. You also know that there's Fahrenheit in the English system, and there's also something called Kelvin. That's part of the SI, that's Systems International. Let me just show you an example of how temperature is connected to kinetic energy. So this is actually a model of a gas. So you can see the particles that are moving around, they have a certain level of energy. It might be hard for you to see, but the level is blue. The average kinetic energy is up to here. The temperature is up to there. I can modify this by decreasing the kinetic energy, which means now I don't see any color there, I don't see any color there. Look what happens to the particles. Look how slow they move. As I increase the kinetic energy, this blue goes up, the temperature goes up. You can see it's what we call a direct relationship. This one goes up, that one goes up. That is a direct relationship. You can see what happens to the particles as I increase them. They're moving faster, they have greater kinetic energy. And how does that work with a thermometer? Well, like for the thermometers you may be used to seeing, the more the particles hit into the bottom of the thermometer, the more energy it pushes that liquid up, the higher the temperature. There's a direct relationship there. So let me show you a little demo that's going to help explain why it's not just hot or cold, right? And why we must use an instrument, right? Because people are not good instruments. People can be easily tricked, right? Whereas a thermometer is not going to. Okay, so we talked about how important it is to actually measure temperature. Here's a little demo, and this is where you can be thankful your dad's not the science teacher because you don't get dragged into these things. Kate, come here and help me. So Kate's my volunteer. She has no clue how I set this up. She just got out of swim practice. That's why the signs are down there so you can see them. She has just walked in the room. This is what I need you to do, Kate. Take 2 fingers and put it in that beaker. Let's use the other hand. And then 2 fingers in this beaker. Okay, what are your first observations here?
That's very warm.
That's very warm. Actually on the hot plate. What do you notice here?
This is very cold.
Okay, so now what we need to do is we need to figure out what would you say here? So using one word, like you already did, warm, cold, whatever. We're going to figure out the middle beaker. So let's do me a favor. Take this hand, put it in there, and just quickly tell me in one word, what do you feel?
Colder than that.
Cold. Okay, so she says cold. All right, now, same thing. Move this hand in real quick. Tell me what you feel.
It's warm.
Warm. How can you have the same beaker feel cold or warm? She's got discriminating observations. That's why humans are not good instruments. That's why you want to use a thermometer, stick it in there, and it'll tell us exactly what the temperature is. But what we've done, we've tricked her, all right, by comparing. This is like a little trick or demo you can do at home. Just be careful that this one is not so hot that somebody burns themselves, and this one doesn't have so much ice in there, it kind of gives it away, but it's got to be cold. Good. Thanks, Kate. Finally, dimensional quantities. They're not basic. They're dimensional. They have dimensions to them. So it's not basic. It's not a single measurement. You're not just doing one thing. You're doing multiple measurements. So down here there are some examples to show you. A good example would be density. If you did that one in middle school, if you want to know the density of something, you don't just do one measurement. D equals m over v, mass over volume. You have to know the mass, you have to know the volume, so there's 2 quantities there, 2 dimensions, in order to find density. Another good one that confuses students sometimes is volume. To find the volume of especially a rectangular cube, you have to take 3 measurements. Volume is 3-dimensional. You have to know the length with a ruler, right? The width, and then the height. And then you multiply those 3 together. Volume is length times width times height. Volume is 3D, right? If you've ever heard that, 3-dimensional, right? And yes, volume can confuse you. If anybody knows how to measure volume with displacement, you have a graduated cylinder with water in it, you drop an object that's not rectangular in, and you use the graduated cylinder for volume, it's still measuring those 3 different dimensions for you, although it does make it easier, but it's still a dimensional quantity. And then 2 other examples. Pressure is how much force per area is on something, and Q, we'll talk about near the end of the year, is the amount of heat. How much heat is within something or needed to make a change. In order to find the heat, you need 3 different variables. The mass, the specific heat, and then how much the temperature actually changed. So all of these are multi-step